So we just did a little bit of practice problems, and now we're going to do Stokes and Gauss's theorem. Okay, so quick overview of the idea that we're going to do first. So we're focusing on the surface integrals of vector fields. And this is related to like integrating a two form. So say you have a surface and it's oriented, then and it has a unit normal called n. You could let f also be some vector field that we know. Then the surface integral of f over s, like by definition, this is the notation, is that you have a double integral over your surface f ds, where ds equals your normal vector times d sigma. Remember we saw d sigma like a few weeks ago for when we were doing the surface integrals. In the two-form language, so this is in vector language, the two-form language, which I have in green, we have that the notation will be the integral of this phi sub f. And so the idea is that if we let S be some oriented surface with a parameterization S, then we have that ds we said is nd sigma, or remember this brings back our like cross product thing, where we took the partial of our parameterization with respect to each of the variables, and then we took the cross product. And so when we solve it with the vector notation, we plugged in, we always did this, found the parameterization, plugged the parameterization into our function, and then we rewrote our d sigma, which is this cross product du dv. In one form notation, you have in the green, we have this two form. And remember that a two form, because it's two, it can eat two vectors. So it's eating this vector and this vector. But what is a two form eating two vectors? Well, it's basically just a triple scalar product. And also, so this is like one notation for the two form. If you like this notation instead, also works. It's like you're, yeah.
I thought a three form is a triple scalar product.
When you have a two form, so you have like your like first component plugged in with your parameterization plugged in, second component plugged in, third component plugged in, and you have this first vector and the second vector. So it's a triple scalar product. So actually in this notation, it's saying the same thing. You have some two form, it evaluated at some parameterization, G. You take the derivative because this gives you a Jacobian matrix with two columns, where each column is your vector, and then ds dt. Any questions on this definition? Okay, let's do an example. So we have that, okay, recall I just put the like canonical form of the two form here, but let's do this example. So we want to compute the flux of this vector field out of the triangular planar region with vertices, I already drew it, P, Q, and R. Use the direction away from the origin perpendicular to the surface as the direction of positive flux. Okay. Let me first start with a starting point, and then I'll give you guys a few minutes to solve it out. So it says that our positive direction, the origin, let's see, direction away from the origin perpendicular to the surface. So like, imagine a line coming out of our paper. Maybe that's not a good, some line coming out, and that's our positive flux. And so we're going to want to use this one form formula, this green formula here. Let me copy paste it. We're going to want to use that green formula somehow. So your steps that you should be thinking about are, we want to parameterize our surface first, rewrite our vector function as some two form, and then follow the formula. 3 steps. Okay, So let me give you guys like 2 or 3 minutes to think about. Yep. Yes. So first parameterize your surface. So write your surface as like g of s, some like 2 variables. Parameterize. Second, you want to rewrite your function as some 2 form, b, because right now it's in vector form, but we're going to need a 2 form so that we can plug in our parameterization. Third step, follow this formula. One, parameterize. Two, write f as for 2 form. 3, formula. Actually, first parameterize it, and we'll go over the parameterization. Okay, does anyone have a does anyone want to suggest a first step for how do we parameterize our surface? So we have this flat triangle, and we want to write the equation of this plane. Do you have that? Yes. So first step is to how do we write an equation of a plane? We need the normal vector. And so how could we get the normal vector? Anyone? Yes. Yeah. So we could take, how do we find a normal? We could take 2 vectors, do the cross product, because we know that the cross product gives some vector orthogonal to it. So it would give us our normal vector. So let's try. So we have some 3 points here. Let's find 2 vectors. So I chose PQ. What is PQ? You do 0 minus 1, 1 minus 0, 0 minus 0. So that would give us negative 1, 1. PQ. Yeah, negative 1, 1, 0, 1, 0. And also PR. So PR would give me negative 1, 0, 1. If I take the dot cross product of these 2 vectors, that would give me my normal vector going outwards. So like some n. And then what's the equation of a plane? Well, plane, by definition, the equation is going to be n dot, you have x, y, z minus some point equals 0. So our n in this case is 1, 1, 1. We can pick any point. It doesn't matter which point you pick. Let's just pick like the 1, 0, 0. This would give me 1, 1, 1 dot with x minus 1, y, z. Or we have x minus 1 plus y plus z equals 0. So the equation of our plane is 1. Or sorry, x plus y plus z equals 1. So we have our plane. That's an equation. That's great. But we need to parameterize it. Right now we have 3 separate variables. But remember in our formula above, we only had g of st. So our parameterization should only have 2 variables. So let's choose some parameterization. If we keep the variables x and y, then x is x, y is y. What is z? I can rewrite my plane equation as z equals 1 minus x minus y. And that gives exactly our parameterization. So this g is our parameterization. And then we need to take the derivative, right? Or the Jacobian matrix. If you take the derivative with respect to x, it's the first column, you have 1, 0, negative 1. With respect to y, you have 0, 1, negative 1 here. Any questions up to this point? Yes. GST is just some general like parameterization name.
Okay, so in all of these cases, we should only use 3 variables?
Yes. Because this plane is in 3 variables right now, x, y, and z. But the point of parameterizing is that we don't want 3 variables, we want 1 less. So we take a variable away.
Okay, so like if there were 2, we would go with 1. But
Mhm.
because it's a three.
Yep. 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 Okay, so now we have our parameterization. And what was my second step? Well, we have to rewrite our vector field as a 2 form. 2 form. So what is the, recall that a 2 form is written like this. The I component corresponds to dy wedge dz. So our first thing should have 3. We should have 3 dy dz plus the j corresponds to the second component. So we have minus 2x dz wedge dy. And the last thing is 2z dx dy. So this is our 2 form. Yep. Oh, 3y. Thanks. Yep.
For the second term, did you iterate dz wedge dx?
Yes. dz wedge dx. So now we have our things. We have a parameterization that works. We have our 2 form, and now we follow our formula. So our formula is this green one, which I have down here. The exact formula. And so we write our 2 form with the parameterization plugged in. So why don't I move our parameterization down a bit so we can see? So I wrote my 2 form. Well, the y is still y according to our parameterization. The x is still x, so I kept it that. But in our 2 form, we had a 2z here. When we plug in our parameterization, what was z? Z was 1 minus x minus y. So I substitute z for that. Then I'm going to multiply by our Jacobian matrix, which I also wrote here. And so remember from last week that one way we could evaluate this, remember what dy wedge dz means. We could take the y like row and the z row from our Jacobian and find the determinant of that. So 3y dy wedge dz can be written as 3y, determinant of 0, 1, negative 1, negative 1. our y and z row. Then you have minus 2x. What is the z wedge dx? Well, that's the z row, which I put first, and the x row next. So the determinant of that. Then plus 2 times this 1 minus x minus y, and dx wedge dy is our first 2 rows, the determinant of that. And so in total, when we simplify these determinants, we get 3y minus 2x plus this whole thing. And then we can keep continuing the integration. Would anyone like me to continue explaining integration? Okay. Oh, yeah.
Can you just explain the y bounds real quick?
Yes. So our parameterization was this g of xy is xy 1 minus x minus y. So we know that x, so we need a bound for x. So x we know has to be between 0 and 1 because that's our problem. It has to be between 0 and 1, 0 and 1. But what is our y bound? So our y bound, well, we know that our z component, our z should also be between 0 and 1. But right now our z is 1 minus x minus y. So I want that, what is the lower bound? I said it equals to 0. That way I can rewrite it as 1 minus x equals y. So our y, let me see. Yeah, the upper bound for y should be 1 minus x according to this. What happens if I set our z equal to 1? So I'm setting it equal to 0 and 1 because this last component can be between 0 and 1. So if I set it equal to 1, then I simplify and I get 1 plus y, or negative x equals y, or y equals negative x. What were the bounds for x? X was also from 0 to 1, so the smallest x is 0.
Is it like when you use using the z as to find the bounds of the consistent way to do it?
Yeah. If you note that if you parameterize it like xz, then like you'd have x, z, and something here, then you would probably want to use this component to see the bounds.
Okay, whatever is like the complicated.
Yeah, whatever is like missing. Okay. Any questions on this problem? All good? Okay. So I was told that, or like in the study guide, you wouldn't have to know like complicated, like in this problem, our positive flux direction was like outwards and perpendicular, so that was fine. We could follow the formula as usual. If you had this other problem, which is recitation question 155, and I can go over this next recitation, this is where the direction into the surface is now positive. So everything goes opposite. And so the idea is that you can still do the same thing as the previous problem, just at the very end, take the negative of it. But you shouldn't need to know like orientations too much this week, I believe. Okay, let's skip that. Let's go to Stokes' theorem. Okay, so Stokes' theorem is that, recall what it means to be a curl. So I wrote the definition of the curl again. And what does Stokes' theorem say? It says that if you have F on some domain D, and we have some surface with a boundary curve C equals like the partial S, this is denoting our boundary, and we have it oriented counterclockwise with respect to the orientation of X. Then what does Stokes' theorem say? It says that if we wanted to find the integral of f dot dr, we could do the double integral over our surface. So now we don't have to deal with some boundary. The surface of the curl of f ds. And so our integrand here has to be a curl in order for us to use this. In the one form language, we would have this integral of boundary alpha f equals integral of our surface. So notice the differences here. Here we have the boundary. Here we have the surface. Here we have two form or one form. Here we have the derivative of the one form. Yeah.
It's because the derivative of the one form is like the curl basically.
Yeah. From the very beginning where I said like the derivative of the one form associated with the curl. So yep, exactly. So that idea was that we did at the very beginning where I was like the derivative of some form corresponds to something that's very important. Okay, and a corollary is that if we have any two surfaces with the same boundary curve, then this integral of that over that first boundary is going to equal the integral over that second boundary. What does that mean? Imagine you have some like cap, right? And we have this red thing as our boundary. So our first surface could be this cap, just the top part. The boundary of that would be this red circle part still, because this is our like cap. Our boundary is like the circle. Our second surface could be the flat circle, and its boundary is also that red part still. So these two surfaces have the same boundary, and so we know by Stokes' theorem that their integrals would be equal. And so what does that tell us? So far we know that if two curves have the same boundary, then the integral of the gradient would equal the integral of the gradient for the other boundary. And that was from proved by the fundamental theorem of line integrals, where for path independence, we needed our integrand to be a gradient field. Now with Stokes' theorem, we're told that in order to be surface independent, so like the integrals are equal, we need our integrand to be a curl field. And so these are our two results that we're learning. Yes. Like the same curve. Yeah, that's the point. So like it doesn't matter what curve you have, the integral is going to be the same as long as you have a gradient. This is a separate, like this part. Oh, this is like if they have the same boundary, it doesn't. Oh, I see. Okay, maybe just like. Wait a second. Oops. Okay, then I guess it could be any, just like two curves. Two curves, C1 and C2. Yeah, but the second one you need the same boundary, just like the example of my cap and then the circle. Yes.
I think the video lectures mentioned that this is like to find the strokes of
So Stokes theorem. Let me see. So Stokes theorem. Flex of the curl. I believe it should be like, we know that this is gonna have to be the curl this part is going to be curl gradient part dA, but flex of the curl. Did anyone else see the flex of the curl somewhere? Okay, I'll look at it during the break. Okay, and so we have these two things. A note is that for in 2D, the Stokes theorem is basically just, or sorry, Green's theorem is basically just Stokes theorem in 2D, like the 2D version of it. And you can see, you can like prove why that is by doing some other parameterization and then using Stokes theorem where you only have like 2D version. So let's do a quick example. So we want to compute the circulation where F is this vector field and C is the boundary of a hemisphere. So you have some sphere, you cut it in half, you just have the hemisphere, and your boundary, you're taking the boundary of that hemisphere. So if we wanted to compute this circulation using Stokes theorem, first way is that we could use this cap and the boundary. So if we want to use Stokes theorem, what are the rules? We need to parameterize and find the curl and then use the formula. So if we want to parameterize our hemisphere is defined as x squared plus y squared plus z squared equals 9. We want to get rid of one of the variables. So if I get rid of the z variable, I just want my parameterization with x and y. Then how could I rewrite z? Well, z I could rewrite as z equals 9 minus x squared minus y squared square root. And so that's how I get my z. Now my z is in terms of x's and y's. What else do we need? Well, we're going to need ds, capital S. How do we get ds? So we saw that ds is that we're going to need the cross product, the like x and the y. So if I compute our Jacobian matrix, take the cross product, I finally get that ds is this like component thing, dx dy. So I've parameterized it and I know what the capital S is. Second step, I want to find the curl. What is the curl? We know that the curl is doing the determinant. So if I do the determinant formula, I end up getting just -2 in the k component. And then finally, I can follow our formula. What does our formula say? We want to do the curl dot ds. So curl was 0, 0, -2. D capital S was this whole thing above I found here. And we're doing the dot product. So when you do 0 times this, it becomes 0, plus 0 times this is 0. You're just left with -2. So we have -2 dx dy, or what is double integral of dx dy? We know that that's the area of our surface. What is our surface? It's this, well, we have a hemisphere right now, but if we think about what is the area like collapsed in the xy plane, because remember we're in xy now, then we just have this disk. The area of this circle is pi r squared, where r is 3, and so we get -18 pi. Yes.
You would have parameterized like the z, but you have a different like
Parameterize. You should still get the same answer. But like your numbers might be a bit different in here. Yes.
In the videos, said yes, they do the normal vector times the arc length.
Mm-hmm.
Is that the same thing?
Normal. Yeah, it's the same. Normal. They do normal d sigma, which is the same.
Like, why would you ever do it that way?
So d sigma is, let me, so like here I wrote like n, so ds equals n d sigma. N is like this n is actually defined as like your actually n is more complicated. It's like your cross product over a length. So that's more about like the derivation of it. I don't think we usually use n d sigma. We usually use ds though, which is that formula. So yeah, n is like a complicated. It's like partial cross product with like some length thing, and then things start canceling out, and you get the same exact thing as ds. Yeah. Okay. Let's take a 5-minute break. So come back at 2:41. And let me pause. Okay. Did anyone have any questions about method 1, where we use the cap? Find the curl. Okay, so in this method, we see that we parameterized like that hemisphere, and it was a bit more difficult because we had this like square root thing. Instead, what Stokes' theorem says is that we could use an easier surface with the same boundary. And that makes our things easier because we can parameterize something much nicer. So instead of choosing that hemisphere, what if we chose the bottom circle to parameterize? So now that's our surface. So I'm going to choose this bottom circle as our surface. How do I parameterize that? Well, now that's just a circle. X squared plus y squared equals 9. Yeah, x squared plus y squared less than or equal to 9, and z is 0. So what's the parameterization of this circle? Well, you have an x, you have an y, and we're on the z equals 0 plane. So no matter what, z is 0. So this is our parameterization, and it's much easier parameterization, right? And so for our steps, parameterize, we need to find, because we have to find ds. So I parameterized it as this, took the Jacobian, do the cross product of our two columns to get 0, 0, 1. And now we know what d capital S is. It's 0, 0, 1, dx, dy. Second step, we need to find the curl. Well, it's the same as our method 1, so I just rewrote what we found last time. We got that our curl is 0, 0, -2. And then now we follow the formula. So the formula is curl.ds. Curl is 0, 0, -2. ds is this 0, 0, 1. And we see that 0, 0, we're left with -2 times 1. So -2 dx dy. Or -2 times the area of our circle now, because our surface is the circle. And that area is pi r squared. So we get the same exact answer. And that was much easier because our parameterization was simpler. It was just x, y, 0 instead of like x, y, square root things. Yep. Curl.
Curl
Mhm.
over a 3D object instead of a 2D object.
Yes.
And then you can just change the or the
It's the same boundary no matter what, but we can change the surface itself, like how we parameterize the surface.
and that you do that by like getting rid of one of the
Yeah, get rid of one of the variables. Yep. So no matter what, you're always gonna like need to find a ds for a surface. Okay, so that was all one form vector language. If you wanted to know how to do this exact same problem in differential language, you have the same exact thing. Like we're parameterizing, if we choose to parameterize that circle, we can parameterize it with t now, like one variable, because we had two variables, x and y. But we could choose to parameterize it as t, and then we follow the one form definition. And you do get the same exact answer anyway. Okay, any questions on that before we do Gauss's theorem or divergence theorem? This? Yeah. So let's see. In the one form language, so the question would say find the integral of the one form, this thing, over C. And note that this is like a 0. So okay, first we want to parameterize it. So right now our circle is x squared. We want to keep this flat surface because that's an easier one we saw from the last exam, like last explanation. Circle is x squared plus y squared equals 9. So I have two variables and z equals 0. So I can choose z equals 0. And then now I just need to deal with x's and y's. And if we wanted to do kind of like a polar coordinate parameterization, I guess, we can choose x as 3 cosine t square cosine t and y as 3 sine t, because that way when we square this plus square this, we're left with 9 times 1, which is 9. So I want to parameterize with just one variable for one form. Okay, then I take the derivative of it. And then what's the definition for one form? So let me scroll up and find this definition. So we have the integral of our boundary, one form, equals the integral of, now we want to take, plug in, so you could either find the derivative, or we can plug in our parameterization and then plug in our derivatives. So it's just like what we've been doing with vector language, where we plug in the parameterization into f, and then we multiply by either like the length or like a dot product of our derivatives. And so what was y? Y is 3 sine t. So I plug it in. Dx is negative 3 sine t. Minus x is 3 cosine t. Dy is 3 cosine t also. So I get negative 9 sine squared t plus minus 9 cosine squared t. Sine squared t plus cosine squared t is 1. So we just have negative 9. And our t is from 0 to 2 pi. Yeah.
So the one form that we're in, is there any similarities like what my last was the one form?
So this example is the same thing as the last example, but in a different language.
Is that the same vector? Or is it
Yes, it's the same vector.
in one form? Oh,
So
cool.
our function was y negative x 0. Yep. Y negative x 0. So we have y negative x 0. So same question, just different language. So I was showing comparison. Any questions on that? Yep. Hmm. If you were given the curl, I'm not too sure actually on that. Let me get back to you on that. Yeah. Okay, so let's do Gauss's theorem. So Gauss's theorem is, let me recall what a divergence is. That's, we're taking the partials of each of the components. So what does divergence theorem say? Let me erase this. Divergence says that instead of doing like some complicated integral, we can do the double integral over some boundary. We can say that it's going to be equal to a triple integral over the region. And then for our integrand is the divergence. So that's why it's called divergence theorem, or we call it Gauss's theorem. In the one form language, we have this thing in the green. Yeah. Where this is the yes, two form. Because remember that the derivative of a two form is associated with the divergence. So that's why we kind of have the divergence as our integrands. And when do you want to use divergence theorem or Gauss's theorem? If it asks you like, what is the flux of F out of the closed surface, like out of the closed surface, then you want to use divergence theorem. But it's if it asks you like what is the flux of the curl, oh here's the flux of the curl, don't use divergence theorem. That's not a divergence theorem question. So I have an example. Compute the flux, this, where this is your vector field, your surface is this, or like your region, outward. So compute the flux outward. And we see that, we know that just from this language, it's a divergence question because we want it to have like some flux out of somewhere. And it asks you to compute the flux outward. So the language is correct. Okay, so what does divergence theorem say? Well, it's asking us to find the left side of this equality. So remember that if it asks you for like Green's theorem or Stokes theorem or divergence theorem, they're all equalities. So you need the left side and the right side. So divergence theorem, you want to find the left side, but that's too complicated. So instead, we use the right side because the right side is easier to compute. So we want to compute the left side. We want to compute the integral over some boundary, but instead, let's compute the triple integral over our region with the divergence as our integrand. So what is the divergence of f? Well, we see that's 1 plus 1 plus 1. So it's 3. That was nice. And we're doing a triple integral dv. What is the triple integral dv? That's the volume of our region. What is our region? Well, our region is this. X squared plus y squared plus z squared equals a squared. And we know that that's a sphere. So what's the volume of a sphere? 4/3 pi r squared. For right now, our r is a. And so we get a final answer of 4 pi a squared. Yeah.
Sure.
4 pi r cubed. Yeah. 4 pi r cubed. Okay. Any questions on that? Okay, and where this divergence theorem comes in handy is that, say we wanted to evaluate some flux over a closed surface, where that surface is made up of like multiple parts, yes? Then if we wanted to do additivity, like if we wanted to use the left side of our formula, and we had all those separate surfaces, we'd have to do this like k times or however many times. Instead, divergence theorem makes it easier for us because sometimes we're only going to need to do one integral. So what's an example? If you wanted to compute the flux, where this is your vector field, and now our region is a cube. So if we actually wanted to do this like the normal way with the left side, well, think about, you'd have to do the top as your surface, plus the integral with the bottom as your surface, plus all the sides as your surface. That's like a bunch of integrals. Instead, if we do divergence theorem, what does it say? We want to do the triple integral over our region, which is a cube right now. What is the divergence of our function? I can calculate that. That will be y plus z plus x. And how do we define like our bounds for a cube? Well, that is defined by like what our x, y, and z can be. X can be between 0, 1, y same, and z also the same. So these bounds were nice to find because we have a cube. And then you take this integral and you can like do the integral multiple times to get 3 halves. Any questions on this problem? Okay, sometimes you might be given a surface that isn't closed. So for divergence theorem, it's important that your surface has to be closed. So like the last example with the cap and a lid, that's closed. Say your surface was not closed, then instead we can find some other easy, so like say they only gave you the hemisphere, we can't use divergence theorem. But we could close that surface by putting the lid there. And then from that, we can find the total divergence, find the divergence of the lid, and subtract them to get just the divergence of the hemisphere, like the top part. So the idea is that here we have some entire, we want to find the integral over some non-closed surface. It could be equal to the integral over the closed surface, so it's closed. Plus, it's plus because there's some orientation thing, but you don't have to worry about orientation. Plus the integral of some other thing that we close our surface with. Okay, so let me give an example. So like we want to compute the flux over this vector field where our surface is just our hemisphere, like I just said. So we want to compute just over that hemisphere. We can close this region by putting that lid on the bottom. The lid is going to be negative S sigma. That's my notation. And so we can first, now that it's closed, imagine we have a closed thing, we can find that integral by using the divergence theorem. The divergence theorem would say that we have the divergence of our function, our vector field, which is 1 plus 1, or 2, triple integral of the volume of our region. We now have a hemisphere, so we can find that volume. It's pi r cubed, 4/3 pi r cubed, divide by 2, because it's just a hemisphere. And so we found the integral of that entire hemisphere. But we didn't want the whole thing. We just wanted the top like hemisphere part, not including the lid. However, we can find the integral over that lid part. That lid part, we can use this formula where we have f dot dn or f dot ds. So you can find ds, and we'll see that we end up getting 0 actually. So it turns out that if we add up the parts, well, the integral of just that hemisphere was equal to the integral over the entire closed surface or closed region. And so sometimes this might be a trick that you have to use in future problems. Any questions on this example? Okay, so let me go to this chart that I made, which I like wrote on here, but it's kind of incomplete-ish. So this is just like an overall chart that might like categorize things better. If things are kind of mixing up together, I know things mix up for me. So if you have some like scalar function and you're asked to find like some integral over a curve, you want to use dl. If you are asked to like look at a surface, you want to use d sigma. If you're given some vector field and asked to find like integral of something, then using a parametric evaluation, you have dr as this definition and d capital S as this definition. Notice here that this is the length. This is just like a dot product. So that was from a few weeks ago where one version we did like the length multiplied by the length. One version we multiplied by like a dot product. On associated fees, if you're dealing with some, cross, I mean like when we did, like sometimes we did f of this dot the derivative, or we did like the length. So the length version would be this side, the dot version would be this. Yep, is what I mean. And if you're dealing with a curve, the appropriate theorems to deal with are this one, the fundamental theorem, which we learned like a couple of weeks ago, where if your integrand is a gradient, then you could do f of your endpoint minus f of your beginning point. Then you have the Stokes theorem or Green's theorem for 2D, where you're asked to find this left side. So you're asked to find the integral over this boundary, but that's too hard. So instead, we can do this right side. So this is too hard. I want to compute the right side. Now, if you're dealing with a surface, it's usually going to ask you to compute this. So notice I just like flip these. So for a surface, you're asked to find this, but it's too hard. So instead, you compute the right side. And for surface divergence, if you want to compute this, that's too hard. So instead, we use the right side. So note that all of these are equalities. So you want to include both sides of your equality. Yeah. Okay, any questions on this chart? This chart? Yes.
So again, the DR on the right hand, what is that represent?
R is your parameterization. So like R, you'd have R of UV equals something, something. And dr would be the derivative of that something, something. Derivative.
Can we do this as opposed to like find the DS with the
Yes. So if you have a surface, then it would ask you to find this, but that would be too hard. So instead, we want to find the boundary. So like we had that hemisphere of the lid. So instead, we use this boundary, the outer boundary, and do f dot dr, which is why in this equation, let me see if I did. Yeah, which is why here f dot dr is kind of like doing, what is f dot dr? F dot dr is f with your parameterization plugged in dot the derivative of your parameterization. So that's why in this example here, we were trying to find the boundary, like we use the boundary for it. We just wanted to do f with our parameterization plugged in. So I plugged in what y was, and then our dot product with the derivatives. So the derivatives were there. Yes.
So if you're asked to on circulation, is that when we use the Stokes theorem?
Circulation. It might. Let me see. It also depends on like if it's over a surface or over a curve, but yeah, use Stokes for circulation.
So what is like the difference between green and Stokes?
They're the same, but Green's is the 2D version of Stokes theorem. Stokes is for 3D. So like in my chart, yeah, I wrote Stokes or Green's theorem in 2D. So like they're the same thing. So in 2 dimensions, the Green's theorem just had like you were doing partial of m over y, or I forget the formula, whatever. And this was like the k component of our curl. Instead, for Stokes theorem, now we actually have the full curl. But in 2D, we just had the k component of the curl. And so having that k component in our integrand, that's Green's theorem. So like, so right now Stokes theorem says this. And so we would have, what is the curl of, in 3D, we have M and P. So in 3D, the curl has partial of P over Y minus partial N over Z, comma, negative partial N over X minus partial M over Y, partial N over X minus partial M over Y, like that. Yes, whatever. But if we only had 2 dimensions, in 2 dimensions, I said that the curl, this becomes 0, this becomes 0. So you would just be left with this, which is exactly what Green's theorem says. Yeah.
Isn't it like X and Z in that section?
Yeah, I might have flipped it. Some X and yeah, Z. Okay. Okay, any questions on that? Okay, if not, we can end recitation now. I have a lot of examples of each component of this chart if you want to check it out in the like practice summaries file. Okay, let me stop the recording.